Please pause the video and take a moment to read this important safety message.
Hey, welcome everyone. Part 4 here in our oscilloscopes for the audio bench. Finally, we're going to actually test out some equipment and learn how to use an oscilloscope. What I've decided to do is, this is part 4 in this series, and I think I'm going to have a part 4A, a part 4B, a part 4C, and each of those will be using a different amplifier. I thought I'd start out with a super simple little single-ended amplifier, then I would do a push-pull tube amplifier, and then the third one I thought I would get into a solid-state unit of some type. And that would give me the flexibility if I wanted to add a part D or E later, I could, but I think my original scope here is going to be A, B, and C. What we've got here is just a super simple, it started out its life as a magnavox console amplifier, and there's a thread out here, and I'll put a link below, that Dave Gillespie had made a post a few years back in 2015 where he had modified one of those to actually use some modern transformers here, and made some modifications to the feedback and the circuit and various things, and made a nice little 2-channel left and right stereo single-ended 6BQ5 amplifier here. Looks like it's got a 5Y3 or something here on the front end for the rectifier, and then it runs, they either run a 12AX7 or a 6EU7 depending on how you wire up the heater voltage here for this. So super simple little amplifier, not a lot to it. Someone has taken this one and put it into a new chassis and has swapped over and is using a triad transformer. I actually bought this unit, and you guys may have remembered I showed a repair of it. I bought it off of Audio Karma, wasn't working, went in, figured out what was wrong, and at this point I don't even remember what that was, but we got it working. So I thought I would just use it on the bench today. Okay, a couple things I'm using in the filming of this video, just so you're aware. The same little B&K precision unit, I put it back on my bench. I'm going to be using the 2246 for this one. I thought the push-pull one, part B, we would use the digital Oscilloscope, but I'm going to be using the 2246 here to match up with it. And then I'm going to shift over, and I've got camera mount here for the oscilloscope and a camera mount downward. So we're actually going to mount this little amplifier upside down in this, and I'll be right back. Okay, if you'll notice, I'm using the little B&C adapter piece I showed you in one of the earlier videos, the little stereo to mono adapter here. Just a, one end of this has a pair of RCAs on it, and the other's the 3.5mm, and I'm just feeding it here into this oscilloscope. The other side of this, I'm just simply going to plug into. Super simple little connection there for that. Okay, let's talk a little bit about the dummy load. So dummy load wise, this is a Dale 250 watt 8 ohm resistor, non-inductive, okay? And the reason I like that is, 250 watts is a lot. And by the way, these things are rated when they're heat sinked. So without heat sinking, it probably doesn't go all the way up to 250 watts, something south of that. So I really don't have to worry about, if I had a pair of these sitting here, what to do. This is exactly what I have mounted. I have 2 of those mounted up here inside of this little box. Matter of fact, if I pick it up and show you on the inside, you see 2 of them. It's the exact same 2 resistors as these. Now, this is a 50 watt, and you know what? This is a 5 watt amplifier, so I could easily use this 50 watt resistor right here instead of this big one. Matter of fact, it makes it a lot easier to clip leads onto. Let me show you just a little bit of the challenge of what you run into with working with the bigger units like this. And that's why I have it wired up inside of this box and all soldered up and whatnot. But when you go and you clip one end on here, and I'm just using a banana jack cord here, right? And then we're going to come over here and we're going to plug this into the back of the amplifier. Okay, so all I've got now out of the amplifier going across my dummy load, but then I want to be able to measure it with an oscilloscope probe, so I'm going to plug my oscilloscope probe into port number 1 up here, and I'll come down here and I'll clip onto the red lead right here. But I've got to establish a ground on the other side of that, or I should. So I'm going to end up using my little clip here from my oscilloscope to actually do that, right? So I'm going to clip on here, and then when I go to the other side here, guess what? I don't have enough length to get over there and do what I need. So I'm having to use a little jumper here to kind of extend it. It just gets a little clunky, right? That's all I'm saying at the end of the day. But I've got it all wired up now. So what I've got is I've got this, and just like you'd hook up a speaker, I'm just connecting up to this unit. And now at this point, when I play the music through this, it just goes into the non-inductive load here instead of into a speaker. It's not all that hard. Like I said, probably would have been easier to set up with this. Got the function generator turned on, feeding into the amplifier. I'm coming out of the amplifier, feeding in down here to the oscilloscope probe on one side. For the sake of simplicity for me, I fed the other side out of my little BNC cable up into my dummy load, but I could have just replicated this again on the other side of the bench or beside of this for the other channel, okay? But you can see I've got this probe set on 1X right now. I'm getting the exact same, that's left and right channel you're seeing up here. There you go, I thought I'd make it a little easier to see, but I've got left and right channel both right here. Same amplitude, same signal, scope probe, and using a BNC connector over tied on the two ends of this thing, the exact same. At RF frequencies, could be slightly different story, but at audio frequencies, we're good to use things like BNC connectors for this type of thing. All right, let's get into the amplifier itself. Okay, same as we were before. I've got two signals being fed here on the oscilloscope, left channel, right channel. And I'm just feeding out of the back of the amplifier into the dummy loads like we had talked about before. And what I'm going to do is walk you through a few things that I like to do before I actually get into the amplifier with an oscilloscope probe itself, right? I'm just measuring across the outputs right now. And I like to start out, oh yeah, by the way, a tip, never run an amplifier, I don't care if it's solid state or tube, without something connected to the outputs of both outputs on it. Or if it's a mono amplifier, always have a speaker on it, or a dummy load operating without can cause damage to your unit. So it's easy to do when you're bench testing to hook up one side, forget to hook up the other, things of that nature. All right. We got two signals here, left and right. Measuring across the output is all we're looking at right now. First thing I want to do is I want to vary the input. So I'm reaching up here on my B&K Precision, and I'm just using the amplitude, and I'm going down to as far down as I can go before I lose the trigger on the signal, basically, right? And you see there I'm starting to lose the trigger. And I didn't see anything different between the two, okay? But then I'm going to start cranking the amplitude up. You guys seeing anything? Look at this. Notice the bottom one here. Notice the sharp kind of corners here on the sine wave. Notice they're sharp on the top, but then you get to this one and it's all blurry and muddy here. We've got some rounding going on here, or clipping of our signal on the bottom half here. And there's a lot of things that could cause that. It could be out of bias, could have some leaky coupling. There's a multitude of things that could cause this to do this. But you see here, finally the second one will start clipping, but the first one clips way, all the way back into right there. I can tell a difference. So even about half power of this amplifier or less. So let's take it back down then till we do have nice equal signal, if we can get that. The other thing I like to do is sweep the frequency. Now, I am going to have to reach over here to the time domain to kind of change my time domain to keep up with what I'm doing here, okay? And if you'll notice, at some point my signal gets really flashy on me, right? I'm down to around 100 Hertz right now, okay? I mentioned earlier there's this chop alternate button. Excuse me, I meant to mention it earlier in the previous video and I didn't. You can see here the difference. So this is alternating between two signals here, and it gets really hard to read that when you get way down here, okay? But the chop kind of takes little bitty slices all along the way. So one of them lets a full wave play out, then it plays the next one below it. This one does just a little bit all along the way of each one. So if you're getting down into low frequencies here, You can use that button to kind of help you out. But you know, as I keep going down here in frequency, if you'll notice, one of these is still kind of nice and clean. The other one, it's getting some ugliness on it, right? Which means this thing's not as responding well on low frequencies on one channel as it is the other. And then I'll take it the other direction, right? And I have to keep adjusting this here on the right to kind of keep up with what I've got as I'm sweeping, okay? And I'm up to, right there, I'm maxed out on that scale, so I'm going to flip up to the 10K scale. So I was at 4 kilohertz, there's 6 kilohertz. Alright, I'm at 32 kilohertz and this thing's still looking good. I get way up here at 40 kilohertz and I'm starting to notice how they're squished a little bit together, but this amp was never designed to work at 40 kilohertz. None of us can hear that anyway. By the top end of the audio spectrum for a nice young individual might be around 20 kilohertz right here, and this thing looks really good around 20 kilohertz. You know, my max hearing maxes out around 18 kilohertz. So, but you can see we definitely have, as we get into, right, and notice it's doing better on the high frequencies at a higher amplitude than it does down here at the lower frequencies on this, this higher amplitude here. So we definitely got something different than in one channel than the other, and I believe this is affecting the sound of the amplifier as well, because I played some music through it a while ago with it like this, and I can definitely tell the difference between one channel and the other. Alright, so we've got our amplifier here on the bench. I did fail to mention this earlier, but this amplifier is plugged into my Variac, which then plugs into my isolation transformer, which then plugs into the AC wall outlet. So this amplifier's chassis here is isolated from the earth mains, earth ground in every way, shape, or form at this point. So that creates a problem for me when I'm wanting to use my oscilloscope. Now, if you'll remember earlier, I was measuring with my oscilloscope across two things, from one lead to the other, or across the dummy load, and I was able to read across both sides of it. But if I'm wanting to use a scope probe with just one end and not have to connect up this little connection here, I need to reference my chassis back to earth ground. Now, I've looked at the schematic of this unit, and I've also looked at the unit itself, and I can tell you that the center tap on the transformer here is tied down to ground, right here. And I can also tell you that the signal path ground is tied to ground. If you'll notice, this right here is the ground between the two speaker lugs. If you'll notice, it's tied to a center tap here on this terminal strip that goes right down to ground. Similarly, right here, we're tying our signal path to ground. So the chassis of this amplifier is not different than the signal path chassis or ground. So I don't have to worry about using a differential probe in this amplifier. On a bridged amplifier or a differential amplifier, it'd be a different story. I'd want to be working in here with a differential probe, but I'm okay working with this. But I need to establish ground in some way, shape, or form. So I'm going to take one end of a green alligator clip thing here. I'm going to clip it on ground, and on my oscilloscope here, I am going to simply plug it in here. Now, this will work fine for audio frequencies. If I was working in RF frequencies, I would need to abandon this long ground cord here, and I would need to clip onto the chassis ground somewhere here and then use this unit, and this is just a pain. Fortunately, we're working audio frequencies. You're not going to pick up that much noise through this cord here, not enough to hinder the level of troubleshooting we're doing. So now I'm free to use one hand, keep the other hand, remember, off of this chassis, and I'm free to start clipping into the circuit at various places. Okay, now if you'll notice what I've got here, two oscilloscope probes, right, plugged in over here onto the oscilloscope. And you could do this with one probe, but I like using two And the reason being, I like comparing left to right channels constantly. So what I've done right here is I'm just feeding on the RCA input, where I'm feeding the signal into this amplifier. So in other words, pre-amplifier. And what I'm going to do is crank up the amplitude of the signal I'm feeding in. I'm just wanting to make sure that's as far as it'll go. That's all my function generator will feed in there. What I'm validating is that my source isn't the cause of my problem. Okay, maybe I've got a bad, maybe this little unit right here was having a problem or was bad, or maybe my cable was bad or something. But I have validated at this point that I'm able to feed full signal into this unit and not lose any attenuation on one side or the other. Okay, and what I've done next now is I have clipped onto the grid leads of this 6EU7. So I'm still on pre-amplification, but I'm on the other side of the voltage divider network and the grid leak resistor and the grid stopper resistor feeding into the 6EU7. So I'm into the circuit, but before the first tube. And guess what? What are we seeing here? We're still beautifully matched signal on both sides. Okay, what I've done now is I've came on the other side of, and I just connected them one at a time. I came on the other side of the plate of this tube. So I looked up the tube pin layout for that tube. I came on the other side of it, and then I jumped on the other side of the coupling capacitors, which connect directly to the grids of these two tubes right here. So one comes straight across this coupling capacitor, and I'm clipped on to it right here. The other one comes across here, ties off on this tab, and then it comes down via this red wire and feeds to this point right here. So now I'm feeding over on, I'm post the 6EU7, okay, the first stage of amplification, and now I'm feeding into the actual output tubes, and look at my signal up here. I can move them down on top of each other to compare them. You make them bigger to kind of get precise. You can tell there's a slight bit of difference there between them. I mean, like just a teeny little bit. And all that typically is the difference in maybe resistor values on this stage, or potentially the tube itself. One side's a little weaker than the other. I've not actually measured this tube. So, but hey, this is way close enough for what we're doing here today. So what does that tell me? It tells me I've made it through the input, through the first tube, the driver tube here, made it on the other side of the coupling capacitors, and I'm still matched up quite well here, right? So it must be something to do with these output tubes, okay? And so let's move to the other side of the output tubes. Okay, so now what I've done is I've moved my scope probes over one at a time here to the little wire that feeds over to the red plug here, the positive terminal of the output, and the same over here on the other channel. And lo and behold, check it out. We're on the other side of the 6BQ5 now, and if you'll notice, bottom signal looking nice and clean. This top one got lots of squishiness to it. So now you're sitting here going, I wonder what's going on there. We're going to try one more thing here. Last, what I'm going to do is I'm going to go to the cathode of the output tube, okay? You know anything about cathode on a 6BQ5 layout, it's pin 3. So I'm going to clip onto pin 3 on one side, and I'm going to come over here and I'm going to clip onto pin 3 on the other side of this tube, okay? Now, I want you to watch this. Keep in mind, there is a voltage built up across the cathode, right? And it varies with the AC signal. However, you're trying to bypass some of that with the cathode bypass capacitor, and you're trying to send it off to ground. But watch this. You notice the top signal here stays rock solid, and I probably inverted my probes when I moved them. Notice this bottom one here. What is it doing? Up and down. It's kind of, and it's also having a hard time even there you go. But if you'll notice it, up and down, okay? Up and down. What that's telling me is I've got a problem with my cathode bypass capacitor. It is charging and discharging, charging and discharging. So I've got something wrong with the cathode bypass capacitor. So what I've identified here is this coupling capacitor right here is leaky, okay? And now I'm gonna have to admit to you, I caused this problem intentionally because there was nothing wrong with this amp to begin with. I simulated a leaky coupling capacitor here. I'll show you here. Okay, maybe you can see it. I snipped it loose. But I had put a 4.7 ohm resistor in parallel with this capacitor hidden behind it. And that's what happens when you get a leaky capacitor. Is it builds up internal resistance, otherwise known as ESR, equivalent series resistance, and you'll start having weird stuff going on in your circuit because all of a sudden your capacitor is also acting like a resistor, and instead it should be fairly transparent to an AC signal and let it flow on through and bypass the resistor in the cathode. So your DC bias is established off of that resistor, but the AC kind of flows around it through this capacitor. That's why they call it a bypass capacitor. But I basically made the bypass capacitor null and void here by putting this little resistor in parallel with it, simulating a leaky or bad electrolytic capacitor. Let's test the circuit now that that's out of play. Okay, I hooked it back up to the dummy load, so I'm feeding out of this unit, measuring across the dummy load resistors, and I'm going to increase the input on this. So we're back to where we started, and if you'll notice, I'm able to feed it all the way up here. Let me drop the scale down one time. But you can see both of these, they both start clipping out top and bottom at the same time, which you're always going to have that. You're always going to have when you overdrive the amplifier. You will go beyond the swing allowed on the load line by the tubes, either in the driver stage or in the output stage, and at some point you will enter this state of clipping, right? And that's when you start having distortion come in. But good gosh, we're putting out a lot of power relative to this what we call flea watt amplifier. But you get the point. We've solved the problem. It was as simple as getting the leaky capacitor, i.e. what I bootstrapped with a 4.7 ohm resistor across it to simulate a bad capacitor. And you can see how we chased that down using nothing more than a couple of oscilloscope probes. Didn't even use a schematic. I'll tell you what I'm going to do. I'm going to take you back over and walk you through the schematic real quick just so you kind of know what we did. Alright, if you felt comfortable with everything I did on the bench a while ago, you may not need to watch the schematic walkthrough. You're welcome to. Otherwise, if you choose to drop off at this point, I'll just say thanks for watching. I hope you learned something. I know I had fun making this video. Otherwise, stay tuned. Probably another 8-10 minutes here to walk through the schematic, and I thought I'd break it down this way. So the items on here in red are the things that we did back here on the bench just a little bit ago. If that had not solved the problem, there would have been some next things I would have done with the oscilloscope, and I thought I'd show you those. And then there are probably some things that I would have done with a digital multimeter, or might have been better to use a digital multimeter for than the oscilloscope. So I've got those outlined as well. So let's orient ourselves a little bit to the schematic. Down here at the bottom, we have the power supply. And there's only one power supply for this entire amplifier, and they drew it once down here. It's easy to identify. You typically see something going to the wall outlet here. You typically see a fuse, power switch, transformer. Here we have our rectifier tube. Then we have a CLC network here for filtering the ripple off of this B+ right here, or high voltage signal. And then we've got another CRC here that drops the voltage down a little bit and feeds. So this would feed like the 6BQ5 tube, and this would probably feed maybe the screens. And then there's some other dropping resistors up here in the top that would feed the front end tube or the driver tube. Anyway, the top part of this schematic here, which is, let's just say this is the left channel, they only draw it once on the schematic, but yet in reality, if you go to build this amplifier, you have to put everything that's in this top part in the amplifier twice, okay? And so they just don't show it because it's redundant, but this, let's say this is the left-hand channel. There's also all of this again on the right channel, okay? So let's walk through here. Input, RCA jack. This is where, this is kind of the second place we went. I'm going to go over here to the other side, way over here on the speaker outputs. This right here is what we were measuring. Now, if you'll notice here, the other side of the speaker terminals was actually grounded to the chassis here, okay? So I could have gotten by with actually only connecting the one side of the scope probe to the dummy load on the positive side, and then the negative side would have carried back through the speaker wire back to chassis ground. But sometimes these are floating, so I went ahead and connected both of them anyway, okay? But this is where we started out, and this is where we saw a difference between the left and right channel as we cranked up the amount of input over here on the left, right? So then next, after we noticed there was a difference, we came over here and we connected on this end right at the input, right at the jack, and we validated that nothing upstream, right? It wasn't a problem with my cabling, it wasn't a problem with any of the adapters, it wasn't a problem with the function generator in any way. We had equal signal coming into this point. Then, this is a voltage divider here made up on the front end. It's also kind of the grid leak resistor here and the grid stopper resistor going in here. So I thought, well, let's get on the other side of that just in case there would be a difference between these resistors, right, on one tube versus the other tube on the front end, or one half of the 6EU7 versus the other half of the 6EU7. So we clipped on right here then the grid, the input of this 6EU7 tube. And we had the exact same outcome at this point in time. So that led me to believe I eliminated this. It's all about the process of elimination, and it's all about comparing left and right, because then it's about knowing something is working right and something else is not, and you're going to just chase that until you find it in the circuit. All right, so since my signal was good going into the tube, then we want to look at the output of the tube, okay? And so we looked up the schematic here for the pin out for the 6EU7, and pins 1 and 6 are the plate. And so we could have clamped on right here at the plate, but then we're dealing with a lot of high voltage. So we said, heck, let's just go on the other side of this coupling cap. Remember, this coupling cap allows the AC to flow through, but it blocks the DC, okay? And keep in mind, right here, we got 245 volts sitting here. This is the other voltage divider I was talking about here. The plate load resistor that feeds over here to this, that drops it down to 118 volts. But anyway, we jumped on the other side of this capacitor, so we're not dealing with that big DC offset. We're just dealing with the signal passing through. And so we clipped right here onto the grid of the 6BQ5, okay? That's pin number 2 in this case. So we clipped onto that, and we noticed at this point, we still had good signal. So then, look what all we've eliminated. We've eliminated all of these components right here from being suspect in comparing the left channel to the right channel, right? And then we went over here on the other side and clipped right here. We could have clipped right here on the plate, right? Number 7. Here's the problem, okay? Then you've got 255 volts of DC offset to deal with. And most scopes have, if you push the little AC button for coupling, they can handle 255 volts. So it's not that big a deal, and we could have done that. But it was just as simple for me to clip over here on the other side of the transformer. Either one would have worked. But the bottom line is, coming out of this, we had the problem. So I knew the problem lied somewhere between this red dot and this red dot, and it's probably not the output transformer. I could have easily clipped on the input here and told that. And I probably should have clipped over here on pin 7 of each of these, just so you guys could have seen that the signal had the problem on the other side of the tube, and we would have ruled out the output transformer. I kind of jumped a little bit because I knew it wasn't the output transformer here, and it typically isn't the iron causing your problem, right? So what does that leave? If we're good here up to this point, this red dot, and we're bad on the other side here, there's not much left, okay? Really all that's left to this tube right here is the voltage feeding it, and keep in mind, the same voltage is feeding both sides. So if it was a problem with the power supply here at the 245 volt level, or 245 volt, we would have seen that in both channels more than likely, okay? Unless it was just bad soldering or, wiring or something of that nature. So it's probably not this. Well, that only leaves two components at that point. This resistor and this coupling capacitor. Well, I was trying to solve this with the oscilloscope and not use a multimeter, so I didn't want to pull out an ohm meter and measure that resistor. Instead, I just clipped on right here, right? And I measured and watched what was happening in this circuit. One of them was functioning properly, the other one wasn't, right? And it was really easy from that to dissect it right down to these two components. At that point, you could have pulled out your ohm meter, measured this, and you could have measured some resistance with an ESR meter across this capacitor. That would have told you just what I found out. We had a bad capacitor, right? So at that point, you know, we swapped out this capacitor, i.e. I removed the parallel resistor I put in it that was making it leak, pretending to be leaky here. And we got our bias back in line and whatnot. Now, if I had not been trying to demo all of this with an oscilloscope and I had just been showing you how to troubleshoot this amplifier, there's a couple of things I would have done along the way as well. One, I would have used a digital multimeter earlier on to check these voltages here. I would have checked the voltage at the B+. I would have checked the voltage here going to the screen of this tube, right? I would have checked the voltage here, which should be sitting around 5.7 volts, which causes a negative 5.7 volts bias over here on the cathode. And I would have seen that one of these probably sitting at 5.7 volts. The other one was probably not sitting near 5.7 volts, okay? So I could have figured out this a little quicker with a digital multimeter right here, and I could have validated my voltages were in spec. But let's say that it wasn't this capacitor, and we needed to keep troubleshooting this amplifier. What might I have done next to figure out what was wrong? Well, really, there's nothing left in this amplifier other than the feedback loop here, right? So this is a negative feedback loop, comes across, right? Here's a little bit of, I think this is a Zobel network made up here. Comes across, goes through this scenario here, comes down, feeds back in here to the cathode of the original 6EU7, and it looks like there's 17 dB of negative feedback there. Well, I would have clipped my O-scope here and compared left channel to right channel. Is there something along here causing me a problem, right? I would have clipped then on the other side of this 300 picofarad and this 10K over here to see, is something there causing me a problem? So if we'd gone through all that, you know, at that point I'd be left with, you know, probably go test these tubes. Could be a problem with one of the tubes, you know, really weak or, you know, acting up type thing. You know, beyond that, I would probably just repeat my steps until I and fine tune in a little bit until I found the actual problem. So, all right, guys, I'm going to call this a wrap. Hopefully this is what you're looking for. I'm trying to make these super practical, not only showing you what I'm doing on the bench, but also trying to walk you through the troubleshooting logic I use here. Hopefully trying to make you guys better troubleshooters yourself. And I'm not saying I'm perfect. I've just done a lot of this. And I'll tell you, this whole thing, it would have taken me as long to put this amp on the bench and get it in the rack and hook it all up and get all the test stuff set up. Almost as long as it would to have taken to solve the problem. This is probably a 10 to 15 minute solve at the most here on the bench. So you saw the logical steps that got you there very quickly. All right, coming up next will be a push-pull amplifier. Then I'm going to try to do a solid state, a Marantz unit or something or another and walk through it. Give me some feedback down below. Is this what you're looking for out of this series? If not, I can course correct a little bit and adapt in the next ones. Oh yeah, by the way, in the next two, I'm not going to drag you through the weeds that I did in the beginning of this one, you know, showing you the whole setup and talking about the isolation transformer in the ground and all that. I'm just going to jump right in on the bench to what's the problem and how we're going to go about solving it. So thanks for watching, everybody. Hope you're having fun. I know I'm having a blast. We'll stay at it.